So for today's discussion, we'll be doing a series of constant terms and their convergence. So this is lecture 7 in our Math 22 course. So quickly, let us recall what a series is. So you have um, a sequence of numbers, okay, a sequence of numbers, A1, so A1, A2, until you have AN and then etc. So this is a sequence of numbers. Okay. So it's an ordered list of numbers. And then if you add these numbers, here you will have n equals 1 up to plus infinity of a sub n. Then this is called a series. Okay. So very quick recall of the definition. And this, look at this is a sum of infinitely many numbers. So this, this series may or may not have an actual sum. Okay? So if it has an actual sum, then we say that the series is convergent. And if it does not have an actual sum, then the series is said to be divergent. Okay, and how do we get this sum if it exists, or how do we know if the sum exists or not? So to do that, okay, we recall our kth partial sum. So this is equal to A1 plus A2 plus until AK, or in summation form, this is sum from n equals 1 up to k of ak. So this is called a sequence of partial sum, okay? Or the kth partial sum, not really a sequence. If you collect all of these k's, okay, then you have a sequence of partial sum. So this is the kth partial sum, okay? And if the limit exists as k approaches infinity, so let me write it here. If limit of sk as k approaches infinity exists, say you have your limit of sk, limit as k approaches infinity of sk, say this is equal to s, okay, then we say that the series sum a sub n from 1 up to infinity, this is equal to s. Okay, so the limit of this kth partial sum will be equal to s. We say the series is convergent. We say a sub n is convergent. Okay. Now, one of the special series that we discussed during the lecture is what we call a geometric series. So let us recall what a geometric series is. We have, so in here, geometric series, geometric, let's see, geometric series. So we write this series in the following form: summation n equals 1 to plus infinity of a r to the n minus 1, or you have summation n equals 0 to plus infinity of a r to the n. So whatever is fine. Okay? So in a sense, if you found this, if you found the series to be of this form or of this form, then you have a geometric series. Okay? Of course, if you remove some of the first few terms, say you started with n equals k, and then it goes to plus infinity, you still have a geometric series. Okay? But you can convert that. If you started with n equals k, you can convert that into this form, either this one or this one. But uh, this particular form or this particular form, you have to make sure uh, to use it or to write the series in these forms in order to get the actual sum if it exists. Okay, so if absolute value of r is less than 1, then the series summation of n equals 1 to plus infinity of a r to the n minus 1, this is equal to a over 1 minus r. Okay? So take note of that. N equals 1 to plus infinity, a r raised to n minus 1. Of course, you will see also maybe you have n equals 0 to plus infinity, but you have a r to the n. And they're the same. A over 1 minus r. Okay? Do I have the correct formula? So, in any case, let us work on the examples now. Of course, if you have, if I did not say the other condition here. Otherwise, okay, if absolute value of r is greater than or equal to 1, okay, then the series a r to the n is not convergent. Okay, or let's say it's divergent. Let's write divergent. So is divergent. Okay, so let us work on the examples that I have here. First example, determine whether the geometric series is convergent or divergent. If it is convergent, find its sum. So look at this, it's already mentioned that this is a geometric series. So all we need to do is to find the r and the initial term a, correct? And then if the absolute value of r is less than 1, then we compute the sum. If it is greater than 1, then the series is divergent. So in here you have a1 equals 10, a2, this is equal to negative 2. Although we only need a1 and a2, let's just verify that this is a geometric series by looking at also a3, 0.4, and also a4. So a4, this is negative 0.08. So your r, this is equal to a2 over a1. So a2, it's what? Negative 2 over 10. So this is equal to negative 1 over 5. And then you have your a2 or a3 over a2. So a3 over a2. So a3 is 0.4 divided by negative 2. Okay? 0.4 divided by negative 2, that's negative 0.2. But this is also negative 1 over 5. And you can verify that a4 over a3, this is also negative 1 over 5. So which means our R is negative 1 over 5. Our initial term here is 10. So this guy here can be written as the sum as from n equals 0 up to plus infinity of the initial term. It's 10. Okay. Oh, since I am using a sub 1, let me start with n equals 1 here to avoid confusion. So you have here 10, that's your initial term, and then you have times negative 1 over 5 times negative 1 over 5 raised to n minus 1. So notice, when n equals 1, negative 1/5 raised to 1 minus 1, that's raised to 0, that's your 10, that's your first term. When n equals 2, negative 1 over 5 raised to 2 minus 1, that's 1. So 10 times negative 1/5, that's negative 2. And then you can continue. So your pattern remains um, in this formula or in this form. Okay? So we have R equals negative 1 over 5. Your A equals 10. So this guy here, okay, this guy here, it's equal to what? A, which is your 10, divided by 1 minus negative 1 over 5. That's your R, correct? And therefore, this is what? Simplifying, you will have 10 over 5 plus 1. 5 plus 1 over 5. And this will give you 50 over 6, or you will have 25 over 3. So this is the sum of your series. Okay? Are we good? Question? Okay, so let's look at the next example. So same example or same question. We want to find or we want to determine whether the geometric series is convergent or divergent. If it is convergent, find its sum. So in here, you can do as in before, but let's just, since again, it's already a geometric series, try to verify that this is indeed a geometric series. So I will leave you that part, but I will write A1 and A2 so that I can find R. R is equal to what? A2 over A1, and this is equal to negative 4 over 3. Okay? Negative 4 over 3. But this means what? Absolute value of R, this is equal to 4 over 3, which is greater than 1. Okay? And since this is greater than 1, this means this series here is divergent. So this series here is divergent. Okay? All right. Just for completion, in the previous problem, I will write that absolute value of R, okay, is 1/5 and it is less than 1. Okay, so in here, absolute value of R, this is 1 over 5, which is less than 1. That's why we can apply this, okay, just for completion. Okay? For the next problem, determine whether the geometric series is convergent or divergent. If it is convergent, find its sum. Now it is already in the closed form. Okay? Or is this the closed or open? But anyway, it's already in this form, summation form. And we clearly see that the initial term, it's 12, and the R is 0.73. And notice that it's written in our form, in our basic form, where we can apply directly our formula. Okay? So what I'm saying is, in this form, R, this is 0.73, which is less than 1. So let me put the absolute value here. Okay? Which is less than 1, and therefore, we can apply the formula directly or immediately. So this means your A, okay, the initial term is when the exponent here is 0. So we have n equals 1, definitely that's the 0. That's the 0 exponent here. So A is equal to 12. And then for the denominator, you have 1 minus 0.73. Okay? So if we do this, we will have 12 over 1 minus 0.73. That's 0.27. So you can use your other methods, like maybe making this a fraction and then simplify. Okay? So in here, what we can do is to what? Multiply this by 100 over 100, which means we will get 1,200 divided by 27. And this is divisible by what? By 3. Both of them are divisible by 3. So you will have 400 divided by 27 divided by 3, that's 9. So we have this. So this is in lowest term already. So that's our final answer. So that's the sum given by this. Okay? And the next question here, we want to find the sum from n equals 1 to plus infinity of e to the 2n all over 6 raised to n minus 1. So, look at this. Okay, look at this. It's not in our form so that the formula can be applied immediately. So you have to work on this. Try to rewrite it in either, again, let me just write it here. Try to rewrite this series in either a to the r raised to ar raised to n, and from 0 to plus infinity, or your summation a r to the n minus 1 and from 1 to plus infinity. Okay? So that's what we're going to do. And if you look at this, loss of exponents, so you have here summation n equals 1 up to plus infinity. This guy here, you can write it as e squared to the n divided by 6 to the n minus 1. Now notice, n equals 1, here n equals 1, so we need our ratio to have exponent n minus 1. 6 has exponent n minus 1 already, but e squared has exponent n. So we adjust this. We take out one of the e squareds. Okay? So this guy here can be written as summation from 1 up to infinity e squared times e squared raised to n minus 1 divided by 6 to the n minus 1. Follow? And therefore, we have this. We have this. We combine this e squared and 6 into one single exponential form so that we will have summation from 1 up to plus infinity of e squared quantity e squared over 6 raised to n minus 1. So it's already in this form where the a, it's equal to e squared. And then your r, it's your e squared over 6. Okay? Question. Now, what is e squared over 6? So what is e squared? So you have what? E squared or e, this is approximately equal to 2 point, maybe let's use 2.7. Okay? And therefore, e squared will be approximately equal to 2.7 squared. And what is 2.7 squared? Is it greater than 6 or less than 6? So 27 times 27, okay? Or 2.7 times 2.7. That's roughly 7.29. Okay? So this guy here is 7.29. Which means that e squared over 6 is greater than 1. So e squared over 6, or let me write this as r. So r in absolute value of e squared over 6, this is greater than 1. Okay? And therefore, this series here or this series here is divergent. So this guy here is divergent. Okay? So what's the point of these four examples? Well, you can use your formula for the sum of the geometric series if it is convergent, okay? And to know if it is convergent, you have to find the ratio, R, okay? If its absolute value is greater than 1 or equal to 1, then the series is divergent. If the absolute value of R is less than 1, then the series is convergent. You can easily check that ratio by knowing what's the initial point or what's the initial term and the second term. You can easily check that one. Of course, that's in the assumption that you know it's a geometric series. Okay? If you still need to know that if it is a geometric series, you have to consider a sub 1, a sub 2, a sub 3, a sub 4. Okay? And assuming that the pattern continues, then you can do your ratio a sub 2 over a sub 1, a sub 3 over a sub 2, a sub 4 over a sub 3, and check that they are all the same. The next point, if the absolute value of R is less than 1, Can we use the formula? Yes, if they are already written in this form, either this form or this form. Okay, and the formula is A over 1 minus R. Okay, so you have to make sure that it's written in this form, just like what we did in here. Okay, question. Okay, let's now look at a more general series. So determine whether the series is convergent or divergent. If it is convergent, find its sum. So I was not able to recall the very first test that you will use. So let me do the recall in here. So recall divergence test. So what does it say? Divergence test. If the limit of an as n approaches plus infinity is not equal to 0, then the series an is divergent. Then the series an is divergent. Okay, so please try to remember this by heart. Try to memorize this by heart. And divergence test, it's a test for divergence. It's not a test for convergence. So like what the lecture mentioned last time, thou shall not use divergence test for convergence. Okay, so the first commandment of series. So let us do this. Here, our an, it's 2 plus n over 1 minus 2n. So in here, you have your an. This is 2 plus n divided by 1 minus 2n. And we find the limit of an as n approaches infinity. And this is equal to the limit as n approaches infinity of 2 plus n divided by 1 minus 2n. Just like the techniques that you know from your Math 21 and the technique that we are using always when we started doing this, you have to multiply and divide the numerator or denominator by 1 over n raised to the highest power that you see in either numerator or denominator. So the highest power that we see for the variable n, it's 1. So we just multiply and divide by 1 over n. And if we simplify this, we will have the limit 2 over n plus 1 divided by 1 over n minus 2 as n approaches infinity. And as n approaches infinity, this guy here will go to 0, this guy here will also go to 0, so that the limit, this is equal to negative 1/2. And this is not equal to 0. Okay? So, that series above, so this series here, summation 2 plus n over 1 minus 2n, and from 1 to plus infinity, this guy here is divergent by the divergence test. Okay? Okay? Question? Okay? Next problem. Determine whether the series is convergent or divergent. If it is convergent, find its sum. So this time we have the sum from n equals 1 up to plus infinity of ln of n squared plus 1 over 2n squared plus 1. Okay? And then let's see if we can use divergence test. Okay? Let's see if we can use divergence test. So we look at an. So in here you have your an. This is equal to ln of n squared plus 1 divided by 2n squared plus 1. But we can write this in this form. This is equal to ln. So what we're going to do is to multiply and divide everything by 1 over n squared. So this time 1 over n squared. Because the highest power that we see for the variable n is n squared. So you have your n squared plus 1 divided by 2n squared plus 1, multiply and divide by 1 over n squared divided by 1 over n squared. And from here, we look at the limit of an as n approaches plus infinity. So what is this? Limit as n approaches plus infinity of ln of. So here, let's distribute that 1 over n squared. We will have 1 plus 1 over n squared divided by 2 plus 1 over n squared. And as n approaches plus infinity, of course, this will just go to 0. This will also go to 0, which means that this is equal to ln of 1 half. And therefore, this is not equal to 0. And therefore, this series here is divergent. So by divergence test, let me write now this. So by divergence test, summation of ln of n squared plus 1 divided by 2n squared plus 1 as n runs from 1 up to plus infinity. This guy here is divergent. Okay? So there is a question here. Sir, so bukod pa po yung kung may limit siya sa kung divergent. Okay, so yung kinukuhaan natin ng limit ay yung mga terms. Kung saan pumupunta yung mga terms. Okay? So, bukod pa yon sa ano yung kapag inad mo na yung mga terms. Okay? So, you are looking at an only. And then you are looking at the limit of an only. Okay? Other question? Okay, so let us go to our next problem. Here, determine whether the series is convergent or divergent. If it is convergent, find its sum. So sum of 1 over e to the n plus 1 over n times n plus 1. So we have a sum of terms here. So one way to do this is to, well, the first step in finding the sum, if this is convergent, is to determine whether separately the series sum equals 1 up to plus infinity, n equals 1 up to plus infinity of 1 over e to the n, and the series sum n equals 1 to plus infinity of 1 over n times n plus 1 are both convergent. Okay? If one of them is divergent, then what was the theorem? If one of them is divergent, then the whole series will be divergent. Okay? I want to ask something. What if both are divergent? What if both are divergent? Okay? If both are divergent, what do you think will happen? The series is convergent, the series is divergent, or inconclusive? What do you think?
Inconclusive, sir.
Inconclusive. Any other answer? So here, you go to the reactions. You know where the reaction is. That's where you put your either thumbs up or your check X or thumbs up or raise hand. So if you think, listen very carefully, if you think uh, that case, both are divergent. If you think it is convergent, okay, put a check mark. If you think it is divergent, put an X mark. And if you think inconclusive, put a thumbs up. Everyone, I want everyone to answer. Uh-huh. Geez, I should know how to do the poll here. I'll try to look at that later. So I think it's a mix. Some are saying divergent, others are uh, saying that it's inconclusive. The answer is it's inconclusive. There are, if you have something like this, you have sum inside the summation symbol. You try to separate them. You can have both of them divergent, but the answer to the series is convergent. Okay? Or if you separate them, both of them are divergent, then the answer to the whole series is still divergent. So it's inconclusive. Let us answer this first, and then I'll give you examples of both cases where if you separate, both divergent, but if you combine, could be convergent or divergent. So let us separate these two guys here. First, you have the sum 1 over e to the n from 1 up to plus infinity. Take note that this guy here, you can write this as the sum from n equals 1 up to plus infinity of 1 over e raised to n. Okay? And in here, it means that your r is equal to 1 over e, and this is less than 1. If you think, if we write the absolute value, it's still less than 1. Okay? But we have here n equals 1, the exponent of 1 over e, it's n. So you have to adjust, so we can use the formula directly. So in here, you have sum from n equals 1 up to plus infinity of 1 over e times 1 over e to the n minus 1. And this means that your a, the initial term, it's equal to 1 over e also. Which means this guy here, it's 1 over e divided by 1 minus 1 over e. Okay? Simplifying this, you have 1 over e divided by 1, or e minus 1. E minus 1 divided by e. Or simply, this is 1 over e minus 1. So this is your sum for the first guy. For the second guy, now, so sum of 1 over n times n plus 1 as n up runs from 1 up to plus infinity. You can use your partial fractions. So using the partial fraction, try to work on the partial fraction of this guy here. Partial fraction decomposition. And this is what? 1/2. So 1/2 times 1 over n minus 1 over n plus 1. Do we need the 1/2 here? I don't think we need the 1/2. So you have here n plus 1 minus n. Yeah, we don't need the 1/2 here. Okay? And then, observe, this is a telescoping sum. Are you familiar with the telescoping sum? You actually did it. I don't know, I don't remember if it was mentioned, but this guy here, it's called a telescoping sum. So what we're going to do now is to use the very definition of convergence of series. We look at S sub k. This is equal to sum n equals 1 up to k of 1 over n minus 1 over n plus 1. And this guy here, when n equals 1, you have 1 minus 1/2. Plus, when n equals 2, you have 1/2 minus 1/3. When n equals 3, you have 1/3 minus 1/4. And then you continue this until you have 1 over k minus 1 over k plus 1. And notice, this guy here will cancel the next term here. Okay? So this is the term. The first one that is being canceled is negative 1/2, and then here you will have positive 1/2. And then you have your negative 1/3 and then your 1/3 there. So this guy here will also cancel this. And you expect that this guy here will cancel the 1 next to it. Okay? But observe that this guy here will be canceled. And this guy here will remain. because this one will be canceled if you have the next term. Correct? Which means that this S sub k is just 1 minus 1 over k plus 1. And therefore, S sub k, if we get the limit as k approaches infinity, this guy here, it's actually the sum as from n equals 1 up to plus infinity of 1 over n times n plus 1. So the limit of S sub k, as k approaches infinity, this will go to 0, and this is equal to 1. Okay? So combining this and this guy here, we will get 1 over e minus 1 plus 1. Okay? Or this guy here, if you combine them, what is this? E over e minus 1. Okay? Now, I'm giving an example. I'm giving an example where both are divergent, but the actual sum is convergent. And the example is very easy. The example is very easy. You have this guy, summation of 1 over n minus 1 over n. You separate them, it's sum of 1 over n minus sum of 1 over n. Each sum 1 over n is divergent. But this guy here, it's just sum of 0. So n from 1 to plus infinity. Here you have n from 1 up to infinity, and this is just 0. So written this way. But sum 1 over n is divergent. Okay? So this one here, it's convergent if it is written this way. If you separate them, each is divergent. What about the other case? Well, tweak this guy here. What you can do is to write it as n equals 1 up to plus infinity, 1 over n minus 1 over 2n. And this is equal to sum of 1 over 2n. As n runs from 1 up to plus infinity. Correct? And this is divergent. So very, very quick answer or very quick proof. Okay? So, question. Let's look at our next example. So, if it is convergent, find the sum. We have this, and again, we'll be doing telescoping sum if possible. Okay? We start with 1, or we have 3 over n times n plus 3. Try to check that this guy here is 1 over n minus 1 over n plus 3. Okay? This is the partial fraction decomposition of this. Try to work on that, practice. Okay? Which means this guy here, it's just the sum. And from 1 up to plus infinity, 1 over n minus 1 over n plus 3. So again, this is an example where if you separate them, each is divergent. I mean, the sum is divergent. But as a combination, as a whole, we will see that this is convergent. And to do this, we look at S sub k again. So summation of 1 over n minus 1 over n plus 3, n from 1 up to k. So let us write out some of the terms. When n equals 1, you have 1 minus 1 over 4 plus when n equals 2, you have 1 half minus 1 over 5 plus when n equals 3, you have 1/3, okay? You have 1/3 minus 1 over 6 plus when n equals 4, you have 1/4 minus 1 over 7, okay? Let us continue writing this. Plus when n equals 5, you have 1 over 5 minus 1 over 8. When n equals 6, you have 1 over 6 minus 1 over 9. When n equals 7, you have 1 over 7 minus 1 over 10. And then you continue this until you will have something like 1 over k minus 1 over k plus 3. And you do the cancellation. So you have 1 minus 1/4, 1 half minus 1/5, 1/3 minus 1 over 6. And then you have your 1/4 here. This is the first time that we are going to do the cancellation. So 1/4 here will cancel the negative 1/4 there. So this guy here will cancel this. And then here you have the 1/5. We'll cancel the minus 1/5 here. The 1 over 6 will cancel the 1 over 6 here. The 1 over 7 will cancel the 1 over 7 here. And all of these guys here will also be canceled. Okay? But somehow, this term here will remain. Okay? This term here will remain because this term will be canceled somewhere there. If you continue this term will be canceled later on. So this guy will remain. But the point is, you have your 1 plus 1 half plus 1/3 plus something in over k. So here you have 1 plus 1 half plus 1/3, and then you have minus 1 over k plus 3. This is your SK, which means, so SK, we get the limit of this. So limit of SK as k approaches infinity, and this is just your sum as n runs from 1 up to infinity of 3 over n times n plus 3. Okay? And as k approaches infinity, this will go to 0, and therefore you have this. Okay? 1 plus 1 half plus 1/3. So that will be the sum. Just add it and you will get your sum. Question? Yeah. So there is a question. Sir, is it not 1 plus 1 half plus 1/3 minus 1 over k plus 1 minus 1 over k plus 2 minus 1 over k plus 3. That is correct. There's something in here. There's actually some other things in here. But let us put that correction. Okay? So if you completed this guy here, you will get the k plus 1 here. And then you will have your 1 minus 1 over k plus 2. And then minus 1 over k plus 3. Because the next term here, it's your plus 1 over k plus 1 minus 1 over k plus 4. So the 1 over k plus 1 here will cancel the 1 before this term. So yeah, that is correct. In any case, as k approaches infinity, this will go to 0, this will also go to 0, and this will also go to 0. That's a very good observation. Question. Okay, let me do my last example here. So, although we discussed only series with constant terms, let us find this guy. Find the values of x for which the series converges. Find the sum of the series of those values of x. So there is a variable here. Okay? There is a variable here. And this type of series, you will learn this later in the course. Okay? And it has a special name. But we will be able to answer this using only the known series that we have. So notice, this guy here, okay, the series n equals 1 up to plus infinity, this can be written as negative 5x quantity to the n. Okay? And this one is convergent. This is a geometric form, is geometric. Which means we need absolute value. This is our r. Absolute value of r, it's this guy here. It's the absolute value of negative 5x. For this to be convergent, that's the question, must be less than 1. This means the values of x must be less than 1 over 5. So that the series negative 5 to the n, x to the n, and from 1 up to plus infinity, so that this guy here is, or so that this converge. So it's just a geometric series. Okay? This guy here converges. And then you can find the sum. I'll give you that second question. Okay? So any question? So again, that's my last example, and thank you for staying, and have a good day.